Hi, welcome back to our continued discussion of directional derivatives. Now you may recall yesterday we talked about how to find the derivative or the slope of a function on a surface. Typically we can find the slope in the x direction or in the y direction. But most of the time we don't always move horizontally or vertically. We might move at some sort of angle. And yesterday we discussed how we could find that derivative on a 3D surface in any direction. And you might recall we called that duff. We called that duff, right? And duff really meant for us it is the directional derivative. And what that meant for us is it gave us the derivative or the slope, right? You can find the slope of the function f, which is a function of x and y, or z, multiple variables, in the direction of u. Now, if you look at the graph over here, that's kind of like saying right here. Imagine we have this curvilicious surface, and we're at this point right over here. And let's say u is represented by this line. Well, we can find the slope of that surface. And that's what we're asked to find. The directional derivative finds this slope in any direction, not just horizontal or vertical. So let's take a look at an example real quick, just kind of review for us. We want to find the directional derivative for this function x squared y cubed, and our direction right here, there's our direction. So we're on the surface, we're facing in this direction, and if you think about it, basically this is saying if there's x and y, in the x direction we go right one, and then we go up one. So we're going in our direction up here. We're going in this direction. And you might easily say, that's pi over 4 radians or 45 degrees. So we're standing on the surface, and on the xy plane we're pointing at 45 degrees. We want to find the slope in that direction. We're on the surface. What's the slope of the surface at that point in that direction? So let's see here. Let's go ahead and solve this. Well, our rule from yesterday, you might recall what duff is. The directional derivative is going to be, what was it? We said it was f of the fx, the partial derivative of x, cosine of theta, plus the partial with respect to y of the sine of theta. So right away we already know we need our partials. The partial with respect to x, that's 2xy cubed. The partial with respect to y is 3x squared y squared. Now I'm going to go ahead and find those partials at our point, negative 2, 1. And if I plug this in into the fx, we get negative 4. The partial with respect to y at negative 2, 1. If we plug that in here, we're going to get 12. Now, we could set this up this way, and that's okay. We can do it that way if we want to. But the other way we can do it, of course, we talked about yesterday, this was a product rule. A dot product. Sorry, I said product rule. Oops. It was a dot product. Now, we do have to be careful. When we do our direction vector, remember, this needs to be a unit vector. That needs to be a unit vector. So let's go ahead and do that. So we're going to take v divided by its magnitude. That becomes, what's that, 1, 1, all over the square root of 2. So we get 1 over root 2, 1 over root 2. So to find duff, to find our directional derivative, we said we can dot product our partials, fx, fy, and dot that with our direction vector, which is this 1 over root 2, 1 over root 2. So taking a look here, we know that this was negative 4, this was 12. Dot that with 1 root 2, 1 over root 2, and we're going to get negative 4 over root 2 plus 12 over root 2, which becomes negative 8 over root 2. And there's our final answer right here. Now remember what this means, what this is telling us, is that this is the slope of f in the direction of u. And that's what that tells us. Right. Very easy to do, very simple to do. You all can do this. I mean, it's not a problem. But let's take a look at today at the partials. A special name that we call the list of the partial is what we call del. This is an operator. It's an operation for us. Okay? And if you notice, it's like an upside down triangle. It's the Greek letter del. Alright? Or as I like to say, a farmer in the del. Now, del is just a vector containing all the partial derivatives. So if I want to find del f, and that's what we say, del f, what we're looking for is a vector. This is going to be a vector with the partials. So my first one, here's my first function, f of x, y equals 3, 7. So the first partial, f, the partial with respect to x is 3. The partial with respect to y is 7. So our del f of x, y will be vector 3, 7. And there we have that. Taking a look at number 2, if I want to find the partials here, I got to find the partial with respect to x. Be careful, they're on the inside. You got a chain rule here. We're going to get the cosine of x, y, weird looking y, and I have to multiply that by the derivative of the inside with respect to x, which just becomes y. The partial with respect to y becomes cosine of xy, but this time the derivative of xy with respect to y is just x. So my del, oh, farmer in the del, is going to become y cosine xy x cosine xy. And the vector, so I close it up. And there's our del. Now, del, if we apply this, becomes something else for us. And we're going to talk about this in the next lesson, okay? On the next day, tomorrow. We call this also the gradient, or it finds something called the gradient. And we're going to talk about that in our next lesson, okay? You can click over there somewhere and you can find the link to that if you want to. All right. So that will find what we call the gradient of a function, which has a very special, unique tool for us. It finds the rate of maximum increase. It finds the direction of maximum increase on a function. Sounds kind of familiar to us, right? Optimizations, yay. All right, so let's take a look at number 3 right here. All right, so we're looking for fx, a partial with respect to x, which becomes just 1 over x, the derivative, natural log is 1 over x, plus, oh no, what's the derivative? Inverse tangent. So let's go ahead over here and try to remember the derivative of inverse tangent is 1 over 1 plus x squared. So this becomes 1 over 1 plus x squared y squared. Times the derivative of the inside with respect to x becomes y. So my partial with respect to y, look, that's just 0. That just becomes 0 because natural log of x, there's no y in there. Plus, this becomes again 1 over 1 plus x squared y squared. The derivative of the inside with respect to y becomes just x. So my del, or you can say it's a del, right? You know, like the singer. And we're going to get 1 over x plus, I'm going to put the y on top, y over 1 plus x squared, y squared, comma, x, oh, for the x on top, 1 plus x squared, y squared. And there's our del operator right there. Ooh, not too bad to do. Now the last one, oh no, I forgot to put a z in there. Whoops, I forgot to put it, hold on here. There we go. Forgot to put my z in there. So let's go ahead and take a look here. The partial, let's just do this real quickly. Let's see if we can do this in our head. You should be able to. Ready? My first one's the derivative with just respect to x. If I just take the derivative with respect to x, we're going to get y z inverse. The derivative with respect to y, whoops, the derivative with respect to y becomes x, z inverse, and the derivative with respect to z becomes, be careful, negative xy over z squared. Remember, the derivative of z becomes negative 1 over z to the negative 2. And there we have our del. And of course, if we take a look up here, remember this is just my partial with respect to x. That's my partial with respect to y, and this was our partial with respect to z. Now, we talked earlier about what's called the gradient. Well, if I want to find the gradient at the point 1, 1, 1. Now remember, what this is going to find for us, remember, what does del find for us? It's going to find for us the directional derivatives. But they are also derivatives. So if I plug in the point 1, 1, 1, that's going to give me this value, 1, 1, negative 1. And this is something we call the gradient. Now in a three-dimensional space right here, or actually in a four-dimensional space, this is going to give us the direction into the fastest rate of growth. We're going to talk more about that, like I said, tomorrow. All right, so go on to the next lesson. I got one more example how we can use del to help us find the directional derivative. We'll talk about that in the next video here.